Okay, so we have an improper integral here. This one goes from 1 to infinity, and it's 1 over x squared plus x. With this one, we're going to have to do, as always, the limit as t approaches infinity from 1 to t. We don't have to split it right away because nothing really here would make this denominator 0 that we have to worry about, in which case we would have to split it. But we don't have to split it into two different integrals, at least for that reason. When we actually try to integrate this, because that's our very next step, right? We try to integrate this now. How do you integrate this? Well, you can integrate by partial fractions. So we are splitting it, but we're splitting it for a different reason than having some major discontinuity here in the denominator, dividing by 0. We're not splitting it for that reason. We're splitting it because we're just trying to integrate it, and we're going to need partial fractions to integrate this. So with partial fractions, we factor the denominator. We factor the denominator, so this is x times x plus 1. And then we have x over a plus x plus 1 over b. These are linear, so we have just a and b. If this was like squared in something, then we'd have like bx plus c. So now we multiply x plus 1 to this side, x plus 1, and we multiply x to this side, bx. This entire thing equals 1. Equals 1 from right here. ax plus a plus bx, which means we get the x over here, and that's a plus b. A plus b x plus a equals 1. A plus b is going to equal 0 because we have no x over here. We have nothing with x. We do have something which is just a constant, which is 1. So a equals 1. A equals 1. And if a equals 1, then b must equal negative 1 because it equals 0. So b equals negative 1. Now we plug this back in, and we have our two fractions. So this is how this looks now. The limit as t approaches infinity from 1 to t, got 1 over x minus 1 over x plus 1 dx. Okay, so now we could integrate this part separately from this part, which is what we wanted. Now it's much easier. So what do we get when we integrate this part? We get the natural log of the absolute value of x. Over here we get the subtraction of the natural log of the absolute value of x plus 1. And remember, for both of these, we're going from t to 1, from 1 to t. And we have the limit as t approaches infinity. for this entire thing. So you could view this as we're having to use it here, and we're having to use it here. So yeah, this is kind of just a little tedious to have to do this, because you have to do the bounds for this one, top and bottom, then the bounds for this one, top and bottom. So it's a total of like 4 things that we're adding and subtracting together. So what happens if we could do this in our minds to make it simpler. What happens if we let the upper bound be t and t goes to infinity? Well, if the natural log goes to infinity, and then we subtract from that letting x be 1, which makes it 0, infinity minus 0 is just infinity. So that would give us infinity minus infinity, because we're letting the limit as t approaches infinity of this go in here, right? So this would be infinity, and then this would be 0. You're subtracting 0 from infinity, you get infinity minus infinity. You would think, oh, I'm done. Or you might have thought, I'm done back here. You might have thought, oh, this diverges. But no, you don't do that. You don't do that. You have to go all the way. We've got natural logs, and it may have an answer. This may converge. This may yet converge. So the way we figure out if this converges or not is by actually just stepping through all the motions, and then you'll see that perhaps it does converge. So let's do it. We have the upper bound, which is the natural log of the absolute value of t, minus the lower bound, which is the natural log of 1, which is 0, because e to the power of 0 is 1. And from that, we're subtracting upper bound minus lower bound of this. So the upper bound is natural log absolute value of t plus 1, and the lower bound gives us 0. No, it gives us natural log of 2. 1 plugged in here gives us natural log of 2. It's not a negative 1, it's a positive 1, plus natural log of 2. Now we could do this. We could subtract and add. We've got just natural logs, and we've just got addition and subtraction. So you've got to remember that with addition and subtraction of natural logs, it's the same as multiplying what's inside. So we have the natural log of t, and we have the addition of the natural log of 2. That's the same thing as saying the natural log of 2t. The natural log of 2t is the same as adding the natural log of t plus the natural log of 2. And we're still taking the limit as t approaches infinity of this thing. And we're still subtracting the natural log of t plus 1. When we're subtracting, it's like dividing what's inside. So we're dividing 2t over t plus 1 with the limit as t approaches infinity. Now look, we have a t in the numerator, a t in the denominator. We can divide the denominator by t and the numerator by t. That's just what we do. We divide by the thing with the greatest power. So in this case, we get 2 in the numerator because we're dividing by t, and we get 1 plus 1 over t. we apply t going to infinity, what happens with this? It goes to 0. You've got infinity in the denominator of this thing right here, and it goes to 0. So we have the natural log of 2. The natural log of 2 is what this converges to. Converges.